Hey folks, today we'll be covering Logit and Probit models, the two standard ways of modeling a binary response once we move past the linear probability model. Recall the main drawback of the linear probability model. Its fitted values are not restricted to the interval from 0 to 1, so they can't always be read as probabilities. So we'll build up a better functional form. We'll cover the Logit model and the logistic function, how to interpret odds and odds ratios, the Probit model, the threshold interpretation that unifies both, and finally, estimation, the likelihood ratio test, and measures of goodness of fit. Let's dive in. To overcome the drawbacks of the linear probability model, we use models that express the expectation of the response as a function of the explanatory variables. Here, pi is the probability that the binary outcome yi equals 1 given the predictor values xi. We model it as a function of a linear combination of the predictors and the coefficients beta. The linear predictor xi prime beta is the same linear combination we have used all along. What is new is the function pi, which wraps around it. If we choose the identity function, pi of z equals z, we get the linear probability model right back. Let's see graphically why that choice causes trouble. With the identity function, the fitted response is a straight line. It keeps rising past 1 and keeps falling past 0, so the model can return a negative probability or a probability greater than 1. That's an unreasonable result. These highlighted pieces of the line lie outside the 0 to 1 interval, and that's exactly what we need to fix. In the context of binary outcomes, we need a functional form for pi of z that always maps into the 0 to 1 interval. An S-shaped curve like this one does the job. We now focus on two special cases, Logit models and Probit models. In logistic regression, also called Logit regression, we express the relationship between the explanatory variables and the probability pi I as follows. The logit of pi I equals the linear predictor. Logistic regression and Logit regression refer to the same model, where the response is modeled using the Logit function. An advantage of the Logit model is that it gives closed-form expressions, unlike the Probit model, which relies on the CDF of a standard normal distribution. So what exactly is the Logit function? For a probability p strictly between 0 and 1, the logit of p is defined as the natural logarithm of p over 1 minus p. Here p is the probability of the event occurring. 1 minus p is the probability of it not occurring. The ratio of the two is the odds of the event, and ln is the natural logarithm. So the logit is just the log odds. Notice the direction here. The logit takes a probability and hands back a number anywhere on the real line, and our model sets that number equal to the linear predictor. But what we actually want is the probability itself, so we need to run the logit backwards. Given the linear predictor z, solve for pi I. Solving the logit equation for pi, I gives the logistic function, 1 over 1 plus the exponential of negative z, which is the same as e to the z over 1 plus e to the z, where z is the linear predictor. This is the answer to the question we just posed. Plotting it, we see why this works. The logistic function maps any real valued number into the open interval from 0 to 1, so no matter what the linear predictor gives us, the output is always a valid probability. That is exactly what makes it suitable for modeling probabilities. Putting the two together, the logit takes a probability to the real line, and the logistic function takes a real number back to a probability. The logit function is the inverse of the logistic function. Applying one to the output of the other returns the original input, so the logit of pi of z is z, and pi of the logit of p is p. As we'll see in the later chapter on generalized linear models, the logit function is the canonical link function for a Bernoulli distribution, connecting the mean response p to the linear predictor. The quantity inside the logit function has a name of its own, and it's worth getting comfortable with it. P over 1 minus p is known as the odds, and the natural log of the odds is known as the log odds. So the logit of p is simply the log odds. Let's put some numbers to it. A probability of 0.5 gives odds of 1 and log odds of 0. A probability of 0.75 gives odds of 3, meaning the event is 3 times as likely to happen as not, and log odds of about 1.1. Notice the pattern. A probability lives between 0 and 1, the odds live between 0 and infinity, and the log odds cover the entire real line. That's exactly the range a linear predictor can take, which is why we model the log odds as a linear function of the predictors. No matter what value the linear predictor takes, the implied probability stays safely between 0 and 1. Let's interpret a coefficient in a logistic regression. Start with a binary explanatory variable, one that is either 0 or 1. Recall the logistic regression model. The logit of pi, the log odds, equals the linear predictor. These are the coefficients we want to interpret. For a binary explanatory variable xij, the coefficient beta j is the difference between the linear predictor when that variable equals 1 and the linear predictor when it equals 0, holding everything else fixed. Notice that the two vectors on the right are identical in every position except the jth one, so when we subtract them, every other term cancels. All that survives is beta j times 1 minus 0, which is just beta j. That is why we can read beta j as the effect of flipping this one variable on, with all the other predictors held at whatever values they happen to take. Because the left side of the logistic regression is the log odds, beta j is a difference in log odds. Concretely, it is the log odds of the event when xij equals 1 minus the log odds of that same event when xij equals 0. So beta j tells us how far the log odds shift when we switch this one variable on. But log odds are awkward to reason about directly, so we don't want to stop here. Let's write that out. Replacing each side of the difference with the log odds it represents, beta j equals the log of the odds when xij equals 1 minus the log of the odds when xij equals 0. And a difference of logs is the log of a ratio, so beta j is the log of the odds ratio. Now exponentiate both sides. The log on the right cancels, and we are left with e to the beta j equaling the odds ratio. The odds when xij equals 1 divided by the odds when xij equals 0. Written out in full, that's this expression. It compares the odds of the event occurring in two different groups. Consider a study examining the effect of smoking on the likelihood of developing lung cancer. Smoking is coded 1 for a smoker and 0 otherwise, and the outcome is 1 if the person develops lung cancer. If the regression coefficient for smoking is 1.2, then e to the 1.2 is approximately 3.32. This can be interpreted as the odds of developing lung cancer for smokers are about 3.32 times the odds for non-smokers. So far we've been discussing binary variables. What if the jth explanatory variable is continuous rather than binary? In the continuous case, since the variable is differentiable, we take a derivative instead of a difference. Beta j is the partial derivative of the log odds with respect to that explanatory variable. Because the derivative of a log is the derivative divided by the function itself, we can also write beta j as the rate of change of the odds relative to the odds. The takeaway is the same in both forms. The regression coefficient beta j represents the change in the log odds of the outcome for a 1-unit increase in the continuous explanatory variable. Equivalently, a 1-unit increase multiplies the odds by e to the beta j. The Probit model is another popular choice for modeling binary response variables. It's modeled using pi of z equals capital Phi of z, where z is again the linear predictor and capital Phi is the cumulative distribution function of the standard normal distribution. The Probit model assumes there's an underlying continuous latent variable that follows a normal distribution. The observed binary outcome is determined by whether this latent variable exceeds a certain threshold. We'll come back to that idea shortly. Here's the Probit curve. Like the logistic function, it's S-shaped and always lands between 0 and 1. Overlaying the logistic curve, the two are remarkably similar. In practice, they usually give very similar fitted probabilities. The Logit curve approaches its limits a little more slowly. The practical difference is computational. The Logit model gives closed-form expressions, while the Probit model requires evaluating the normal cumulative distribution function. Both the Logit and Probit models can be interpreted as having an underlying linear model. This is called the threshold or latent variable interpretation. We assume a continuous variable, y star, which follows an ordinary linear model. Y star represents the propensity or tendency for a certain outcome. It captures the underlying continuous process that drives the binary outcome, but it isn't directly measured in the data. The observed binary outcome is then given by the threshold model. If y star is at or below 0, we observe a 0. If y star is above 0, we observe a 1. Picture y star on a vertical scale. Everything above the threshold of 0 is recorded as a 1, and everything at or below it is recorded as a 0. We only ever see which side of the line an observation falls on, never the value of y star itself. To derive the Logit model from this setup, assume the disturbances follow a logistic distribution, so the probability that epsilon star is at most a equals 1 over 1 plus the exponential of negative a. The probability that the outcome is 1 is the probability that y star exceeds 0. Substituting the latent model and rearranging, that's the probability that the disturbance is at most the linear predictor. And by our logistic assumption, that's exactly the logistic function evaluated at the linear predictor. We've recovered the Logit model. The development for the Probit model follows the same logic, with normally distributed disturbances. In both Logit and Probit models, the objective is to estimate the parameters beta that define the relationship between the explanatory variables and the binary outcome. These are typically estimated using maximum likelihood estimation. It's unlikely that this level of math will be tested on the exam, so you don't really need to memorize all this information. We'll just go over it for completeness. For a dataset with n observations, the log likelihood function for a binary dependent variable model looks like this. Each observation contributes the log of the predicted probability when y is 1 and the log of 1 minus that probability when y is 0. Here, pi of x I prime beta is the predicted probability that yi equals 1 given the explanatory variables and the parameter vector beta. The parameters are estimated by finding the values that maximize the log likelihood, which we do by setting the score equations to 0. The information matrix, the negative expected second derivative of the log likelihood, can be used to estimate the sample variance of the estimated coefficients. For specific cases, such as logistic regression, the information matrix can be derived in a straightforward way. For the Logit function, it's the sum over observations of sigma I squared times xi prime, where sigma I squared is the Bernoulli variance, the predicted probability times 1 minus the predicted probability. To evaluate the overall fit of a nonlinear regression model, we often employ the likelihood ratio test. Quantitative questions using the likelihood ratio test show up in the SOA sample questions, so you'll want to study this topic carefully. Check out the Actuarial Nexus for practice questions using this formula. To run the likelihood ratio test, we test the null hypothesis that all of the slope coefficients are 0, meaning the predictors add nothing to the model. The statistic is twice the difference between the maximized log likelihood of the fitted model and the maximized log likelihood of a model with only an intercept. L of beta hat is the maximized log likelihood of the full model, and L0 is the maximized log likelihood with only an intercept term. Under the null hypothesis, this statistic follows a chi-square distribution with k degrees of freedom, where k is the number of predictors in the model. A large LRT value means the predictors improve the fit enough to reject the null hypothesis. Evaluating goodness of fit in nonlinear models can be challenging, since the usual R-squared from linear regression doesn't carry over directly. The first is the max-scaled R-squared, defined as R-squared divided by the maximum attainable R-squared. R-squared here is 1 minus the ratio of the exponentiated average log likelihoods, and R-squared max is 1 minus the square of the exponentiated average log likelihood under the null model. Note that L0 over n represents the average value of the log likelihood under the null model, the one with only an intercept. Another measure is the pseudo R-squared. It compares the improvement in log likelihood from the null model to the fitted model against the improvement available from the best possible model, where Lmax is the log likelihood of the model with the maximum achievable likelihood with all predictors included. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.